Biology with Dr. E.
Our next topic is atoms and elements. Each element is composed of essentially identical particles called atoms. An atom is the smallest indivisible particle of an element that maintains its properties. Each element's atoms differ from those of all other elements and gives the element its unique physical and chemical properties. Atoms are designated by a 1 or 2 letter chemical shorthand called the atomic symbol. These are usually the first letter of the element's name. For example, C stands for carbon and O stands for oxygen. In some cases, the atomic symbol is taken from the Latin name for the element. For example, sodium is indicated as Na from the Latin word natrium. The word atom comes from a Greek word meaning indivisible. However, we now know that atoms are made up of subatomic particles, namely protons, neutrons, and electrons. The subatomic particles differ in their mass, electrical charge, and position in the atom. This table provides a summary of the properties of subatomic particles. Protons have a charge of +1, a mass of 1 atomic mass unit, and reside in the nucleus. Neutrons have a charge of 0 or no charge, a mass of 1 atomic mass unit, and also reside in the nucleus. Electrons have a charge of -1 and a very negligible mass. From this summary, you can deduce that an atom has a central nucleus containing protons and neutrons. The nucleus in turn is surrounded by orbiting electrons. So, although the electrons have a negligible mass, the strength of its negative charge is equal to the strength of the positive charge in protons. Because of this, all atoms are electrically neutral because the number of protons is equal to the number of electrons in an atom. That is to say, the number of positive charges are cancelled out by the number of negative charges. And you can also deduce that because both protons and neutrons are in the nucleus and only protons are charged, that's why they are positively charged, the net charge of the nucleus is a positive charge. Two models have been proposed to explain the structure of an atom. These are the orbital model and the more simplified planetary model. As you can see here, the planetary model depicts electrons moving around a nucleus in fixed circular orbits or shells. On the other hand, the orbital model depicts electrons as clouds of negative charges. It describes electrons existing in regions of probability called orbitals rather than fixed orbits. The orbital model is more useful in predicting chemical behavior of atoms. However, for the sake of this lecture, we will stick to the planetary model to simplify the concepts. One question you might have is, how can we identify different elements? We know that all protons are alike, regardless of the atom considered, and the same is true for neutrons and electrons. So what makes each atom unique? The answer is that different elements have different number of subatomic particles. To get a complete picture of an element, we need to know its atomic number, mass number, and atomic weight. This figure shows that atoms of different elements differ in the number and type of subatomic particles. A hydrogen atom has one proton and one electron, but no neutrons. A helium atom has two protons, two electrons, and two neutrons. A lithium atom has three protons, three electrons, and four neutrons. Now let's review what these identifying properties are. We start with atomic number. Atomic number is equal to the number of protons in the nucleus of an atom. The atomic number is written as a subscript in front of the atomic symbol. Because the number of protons is always equal to the number of electrons in an atom, the atomic number indirectly tells us the number of electrons in that atom. For example, if the atomic number of an element is 11, the number of protons is equal to 11. Hence, the number of electrons is also equal to 11. The next is mass number. Mass number is a total of the number of protons and neutrons in the nucleus of an atom. So if you know the mass number of an element and the number of neutrons, you can determine the number of protons and by extension, the number of electrons. Next, we look at isotopes. Elements in nature exist as mixtures of isotopes, which are structural variations of the same element. Isotopes are atoms of the same element with the same number of protons and electrons, but differ in the number of neutrons they contain. Because of the difference in the number of neutrons, isotopes have different mass numbers. Isotopes of an element typically exhibit the same chemical properties, but have different atomic masses. The atomic weight of an element is the weighted average of the atomic masses of all the isotopes of that element. Most known elements have at least two isotopes, which have the same number of protons and electrons, but different number of neutrons. The most abundant isotope of hydrogen, indicated here as 1H, has one proton, one electron, and 0 neutrons. Deuterium is the second isotope of hydrogen, indicated here as 2H. It has one proton, one neutron, and one electron. The third isotope is tritium, indicated as 3H. It has one proton, two neutrons, and one electron. Some isotopes are referred to as radioisotopes. Radioisotopes are unstable forms of an isotope because their nuclei contain an excess amount of neutrons. The isotopes are radioactive and release radiation as they decay into more stable isotopes. Radioisotopes usually lose nuclear content in the form of high energy radiation that includes alpha particles, beta particles, or gamma rays as they decay or break down into stable isotopes. The time it takes for a radioisotope to lose 50% of its activity is called its half-life. Radioisotopes typically share the same chemistry as their more stable isotopes. Because of this, radioisotopes are valuable tools for biological research and medicine. Most radioisotopes used in clinical settings are used for diagnosis to localize and eliminate damaged or cancerous cells. For example, iodine-123 is used to determine the size and activity of the thyroid and also to detect thyroid cancers. Next.